Yeah. In IPv6, we saw various things like the size of the address is 128-bit binary, but represented in 32-bit hexadecimal. If one hexadecimal is equal to 4 binary, then 32 multiplied by 4 is what? 128. Correct? 128. So IPv6 is 32 hexabit address. 32 hexabit address. And the 32-bit hexabit address is divided into 8 sections. If you want to divide 32-bit in 8 groups, then in each group how many bits? 4 bits. So 4 hexabits per group. Likewise, we got 8. This is IPv6 hexabits. If you count and see, there will be 32 hexabits. And how many groups? 8 groups. And I told you 1 hexabit is equal to 4 binary bit. One hexabit is equal to 4 binary bit. You got 32 hexabit, which is equal to 128 binary bit. Binary bits. And this 32 hexabit is divided into 8 groups. So if I need to divide this 32 by 8, then I'll get 4. 4 hexabit in a group. Four hexabit in a group. If I need to say that in binary, how many bits? If I have 4 hexabit in a group, how many binary bit in a group?
Binary bit, 16.
16. 16 binary bits. So if you multiply 16 into 8, what do you get? You get the same 128. 128 hexabit. So this is 16 bit. This is another 16 bit. This is another 16 bit. This is how we should understand the size of IPv6. How is 1 hexa 4 binary? Because 1 hexa can be 0. It can also be E. F. F is the biggest one. It can be 0 or F, which is in decimal 0 or 15. In binary, if I want to write 0, I don't need too many bits, but if I want to write 15,
4 bits.
I need 4 bits. So this is why we say 1 hexabit is equal to 4 binary bit. For 1 bit, the biggest value is 15. To write 15 in binary, you need 4. So these things is good to know. It's a fundamental understanding of IPv6 address. And later we saw IPv6 don't support any broadcast services that we have in IPv4. In IPv4, there are a lot of attacks possible today because of the broadcast, layer 2 broadcast, like ARP, DHCP, and so on. We don't have broadcast applications of in here anymore. So This address type starting with 2000, we call this as global unicast address. Global unicast address. So there is a special reservation for multicast. For unicast communication, we use only the address that starts with 2000. As of now, only 2000. There is no 3000, 4000. As of now, we see 2000, 2001, 2002, 2003. That's how the organizations who are in control of this address have started giving to the entire world. According to the region, they give some number, they give some reservation, they give a number like 2003 for a region, 2002 for another region. Now for multicast, you will see all address starting with FF0. This can be anything like FF02, likewise. For example, FF02 colon 2 is routed multicast. FF02 colon 1 is host only multicast. FF02 colon other things, what 9 is what RIP-NG. So there is a reservation for unicast address. There is a reservation called multicast address in IPv6. Example, FF02 colon 9 is for IPv6 RIP. We call this RIP-NG, RIP next generation. Likewise, FF02 5 and 6 for OSPF, FF02 colon A is for EIGRP. Now, along with that, there is another new address type called link local address type, which will always start with FE80. Don't forget this. It will always start with FE80. We call this link local. Link local. FE80. You can put 12 also. Totally 16-bit. Only these bits are reserved. You cannot have any other number. Only these things are masked. The 0 can also be anything, but usually you don't see any number other than 0 there. So link local address always FE80. The purpose of this address is to identify the device that are connected on that link. It can be a multi-point link or it can be a point-to-point link. That doesn't matter. The address FE80 is used by ICMP version 6 protocol in order to discover neighbors that are connected on the link. Neighbor discovery. That is why it is called as link local address. On that link, whoever is connected, there are 4 routers connected to this link. How they get discovered? By using ICMP version 6 link local address. So ICMP version 6 link local address. ICMP version 6 uses link local address to discover neighbor. So there is a unique function to do. You will not be able to ping this address like what you do in normal IP routing. This is not for routing. The address is for neighbor discovery. How is how routers are discovered as neighbor? With a MAC address. Any device, how do you discover them? With a MAC address only you discover them. We don't use the word neighbor discovery in IPv4. We don't use the word neighbor discovery, but we do use another word called ARP. What ARP exactly does is it does neighbor discovery. It discovers neighbor. Please pay attention. You will understand what I am trying to say. It discovers neighbor by doing layer 2 broadcast. Which one? ARP. ARP does layer 2 broadcast in order to discover neighbor. But broadcast is not supported in IPv6. That is why it uses multicast. It uses multicast and also it uses this link local address as the source address. See, whether it is a layer 2 broadcast or a multicast, there is need for a source, there is need to be a source address, there is need to be a destination address. The source address of this device which wants to discover is going to be its own link local address. What will be the destination address? That is going to be the multicast address provided by ICMP version 6. So this is going to be a multicast service. So how neighbor discovery is happening, not by broadcast, but by multicast. So when you do multicasting, it cannot go to anyone other than the right group member. We'll see this in the debug in the command line later. But what I am trying to say here is there are various address types. Link local address, global unicast address, multicast address. We have two more address type, but one is already deprecated, one is already removed from the standard, which we call it as site local address. We used to have this site local. The reservation is FEC0, FED0. These two reservations were made earlier and called as site local address. But now it's removed from standard. They removed it. They don't want to have this address type. The reason is not necessary. You see the word site local, it's equal to your private IP address. Initially, in IPv6, we had this reservation so that you can use it as a private address. But there is no more. It's no more. It is removed. We don't need private IP address now. Why? Because we got plenty of IPv6 address. So there is no need for private, public. Public address itself is too much, more than we need. So there is no need for private. What is wrong in having private address and public address? Private addresses cannot be routed in the public, so you will do NATing. That's a headache. NATing is a headache. So IPv6 don't really encourage NATing. IPv6 don't support NATing. So we don't have NATing in IPv6. No NATing.
So do we have that carrier grade NAT then IPv6?
See, carrier grade NATing is more worse than normal NATing. So no carrier grade NATing, no NATing. The reason is NATing is nothing but changing the source or the destination address for every single packet. Changing the source or destination address on every single layer 3 header. If I'm sending 1 million packet, for each packet I have to open it, remove the old address, put the mapped address, which is very bad approach. Going to take time and processor. Carrier grade NAT is more worst. Carrier grade NAT is doing NATing for the packet which is already NATed. NATing after NAT is what carrier grade NAT. If NATing itself is not acceptable, how can carrier grade NAT acceptable? Most of the countries, they don't know what is carrier grade NATing, except few countries like India, some part of Africa. They only will know about carrier grade NATing, because these are the countries which don't focus on quality, which want only money. So they will do NATing in the cost of customer. For the customer, they say, hey, look at this, we have given this much bandwidth. But when you do NAT after NATing, the performance is going to go down. And who is going to pay for that? Customer is going to pay for that. So carrier grade NATing is not a good solution. When we speak carrier grade NATing in some countries, they really hate us. They don't like to listen. As soon as I say it is NATing to the traffic which is already NATed, then they get really pissed off. They know what is NATing and how bad NATing is. And when I say you need to do NATing again for those packets which is already NATed, this is what carrier grade NATing, they get really upset. What? No, we don't want. I've tried in some countries. No one is interested in carrier grade NATing. Anyway, definitely IPv6 never supports carrier grade NATing. NAT, the word NAT itself is not in IPv6 except one place. What is that? For time being, there is one NAT solution, but no one is ready to use that. But there is one solution for migration period. We call it as NAT PT, NAT protocol translation. That is not NATing between one IPv6 address to another IPv6 address. NAT PT is not translation from one IPv6 address to another IPv6 address. It is not. Then what it is? It is protocol translation. IPv4 to IPv6, IPv6 to IPv4. That is NAT PT. But that is not a recommended solution for migration. That can be used as one solution, but not at all a recommended solution. No one uses NAT PT. Instead, we'll use dual mode. We'll talk about those migration thing later. NAT PT is not at all a solution used in production, though it is a solution which is available theoretically. but nowhere you will see practically being used. Yeah. So NAT-PT is not a solution. So no natting is in IPv6. What is your question now? Do you have any question, Girish? Okay.
No, sir. Thank you.
This FEC0, FED0 also you can forget. This is no more. Earlier, there was a reservation like this called site local address. But this is not a routable address. You need routing. So they removed this from the IPv6 standards. We got one more called Anycast address. Anycast is nothing but nearest destination. That's all. Anycast. So any address you can take and you can repeat it in different location. Same address you can reuse in different location if they are providing same service. For example, DNS. For example, DNS. So DNS service is what everyone needs, the entire world needs. Instead of having different IP address for DNS servers, you may have 1000 DNS servers in different location. You keep totally you have 1000 DNS server, maybe 3 in Asia, 3 in Europe, 3 in Middle East, 3 more in Africa, 5 more in US. Now all this will have same IP address. All this will have same IP address. If I'm in India, then I'll use that address, and when I check the routing table, it will take me to the nearest one. My router will take me to the nearest DNS server. For those in London, though address is same, they will not be coming to the same DNS server which I am coming. They will not use the same DNS server which I am using. Even though the address is same, the nearest will be serving us. For Europe, there is one, let's say in Germany, in Frankfurt, we have one DNS server. And there is one DNS server in Bangalore. So when I ask for DNS service, response won't come from Frankfurt, Germany. It will come from local Bangalore. But the address is same. In case if Bangalore DNS is down, the next nearest may be from Dubai. I'll get the reply. But address is same. This type of address that which you reuse in various location is what called as Anycast address. Anycast.
So how
It's
the routing
nothing.
will
It's
happen, sir?
very simple routing. You see, I'll take one simple example to understand this. We have a DNS server here. We have another DNS server here. All right, so there are some people connected here, here. Here. Let's say the IP address of this one is 2000 colon 1 colon 1 colon colon 1. This is also same 2000 colon 1 colon 1 1. Now the routing table of this router will say this is the shortest to reach, isn't it? OSPF will say this is the shortest. Will it show this one? If the cost is one here, one here, one here,
No.
it's going to point towards this direction. So when this guy goes for DNS, he will be directed towards the right hand side, not the left hand side. Routing table will take care of it. The OSPF or any routing protocol will be used. Likewise, the person who is here, when he looks for DNS, it will direct him here because this is very cheaper. And in case if this is down, the routing table will not have root here. This routing table here will take him here. If this comes back again the shortest path will be updated into the routing table. He goes here. You see? So that is not a deal, that's not a IPv6 burden, that is routing protocols job. The nearest. You can simply change it as 8.8.8.8, now you'll understand. This routing table will have a route for the nearest one, this one. If this fails, it will this routing table will show this time because this is gone. It checks the database, link state database, it finds another direction, it will put you to the left hand side path. That's taken care by the routing protocol and the router. So what I am trying to say is you can use an address repeatedly in various places, and we call that address as Anycast address. Right now, this is not the first class. This is like third or fourth class in IPv6. Routing is very easy. I tell you, you need.
Yeah,
Yes.
yeah, yeah. I'm sorry to disturb.
So
Is
let's
this
say we got some routers like 1, 2, 6 routers. Let's say we have 6 routers. Now, the loopbacks I would like to write like this: 1 colon 1 slash 128. 2 colons should come. 1 colon 2 slash 128. Because I am fully masking, these two are unique address. 1 colon 3 slash 128. 1 colon D slash 128. I can say here C. Nothing wrong. B. A means 10, no? 10, 11, 12, 13. Likewise here I'm going to say 1 colon E slash 128. 1 colon F slash 128. Now we need to reach these loopbacks from one router to another. We need routing. For that, there should be some network in between. So I say here 2000 colon EB colon slash 64. Here I'll say 2000 colon BC colon 64. 2000 colon CD colon slash 60. So likewise, I'm going to put the IP address. Here what it will be the IP address? 2000 colon DE colon D slash 64. And here it is going to be colon E. Likewise here I'll say 2000 colon EF colon F slash 64. And here it is going to be E. See, when you have these many routers, definitely you need routing. We need routing. Either you can go for static route or dynamic route. We'll do all static route, OSPF, EIGRP, ISIS, BGP, EIGRP. All we are going to do in this topology. So let us go to command line, bring this 6 routers, put IP address same what we discussed, and we'll start from there. 6 routers, we need 1, 2, 3, 4. All right. Now, as we already spoke, we are going to have loopbacks like this. 1 colon A slash 128. Lowercase, uppercase, that doesn't matter. Let's take only 4 router now. Later we'll add for more for routing protocols. Between R1 and R2, I'm going to take 2000 colon AB colon slash 64 network. 64 is the network. Here it is going to be PC. As I said earlier, uppercase, lowercase, that doesn't matter. For no reason it is going 100%. I'm not sure why. So we got the console. Let's begin. So I'm going to put the IP addresses. First I'll put it directly on the router. Later I'll use a notepad to do it. Interface loopback 0 IPv6 address 1::A slash 128. Interface F0/0 IPv6 address 2000:AB::1 slash 64. Now if you check now, there will be two more addresses dynamically generated and assigned. One on the loopback, another one on the fast Ethernet. That is what link local address. So we are going to see link local address dynamically generated. I told you link local address will always start with FE80. Link local address will always start with FE80. And we no need to configure this, but it doesn't mean that you cannot configure. You no need to configure because it is going to be dynamically generated and given to you. See, show IPv6 interface brief. It's very easy. Commands are very simple. If you know IPv4, you need to put IPv6 instead of IPv4 wherever you want to verify. Like, for example, I'm here trying to see the interface status for IPv6. So I'm saying IPv6 interface brief instead of saying show IP interface brief. Now, if you notice there on the top, we gave this address on the F00 interface. We did not give this. FE80 is the link local address. This address is dynamically generated. And this is not the address that we will be using to deliver some packets, to transfer some traffics. For communication, we will use only 2000 series address, global unicast address. And what is the purpose of FE80? Only for neighbor discovery. They're internally used for neighbor discovery. They're dynamically generated, they're internally used. You will also see a link local address for loopback interface which we created. This is the only address we gave, but this is also generated to identify this loopback interface. Okay, now let us go to router 2 and put configuration. As I said, I'm going to use a notepad. It's my CPU. Okay, here I'm going to change this as B. This is going to be 2 here. And we got another interface on the same router, which is 1, and this is BC 2. That's it. This goes on router 2. So now for router 3, this is going to be C, and F01 on router this one is 0. This is going to be BC : 3, and this is going to be CD : 3. So this is on router 3. Okay. Now let's do one more router. And this is going to be 004. This is going to be DE4. Anyway, we are not going to use this side of R4. So next is we are going to learn static route. Pay attention. On R1, we don't need to write a precise route. We can use a default route. How to write default route? IPv6 route colon means what, 00000 all bits 0 / 0 subnet mask. Subnet mask can be anything. Destination IP address can be anything. That is what default route, right? Any network, any subnet mask. Where do I need to send? I need to send to 2000 : AB : 2. Do you agree? Do you agree this gateway address? This is what we gave on router 2 F00. Okay, writing default route is only this much. Let me show you on R1. Right now, if you check show IPv6 route, you don't have a route to reach other networks. You have only one physical connection, another one loopback. LC means loopback. I'm going to write this default route. And now if you go and check the routing table, you got a static default route. Any network, any subnet mask, send it to this guy, router 2. Assuming we don't have router 5 and router 6, I'm going to write default route on R4. Can someone tell me what I should type? I want to write a default route. Give me the command. IPv6. Yeah, IPv6
towards R3
route any network,
route
any subnet mask,
colon
send it to 2000 colon
0
D colon
2000
D. Yeah. We
DE
are in R4. Assume there is no R5. Towards R3 you should send. CD colon
R3
3.
PD
I told you assume that we don't have router 5
3.
and router 6. So for R4 this is the direction. R3 is the direction. Okay. We have written default routes. Show IPv6 route. You got a default route. Go up. In IPv4, default route will have a star. In IPv6, you will not have any star. Alright, there won't be any star. What is next? Now let us go to router 2. Router 2 don't know about 1 colon A. So I'm going to say IPv6 route. If you want to go to 1 colon A slash 128, you need to go where? 2000 colon AB colon 1. And if you want to go to B, sorry, I'm already in B. If you want to go to C, 2000 BC 3 you will give no. And for D also you will give the same thing. So what you can do is instead you can add a default route here for all the rest of the network. For all the rest of the network, you just take R3 as a gateway. Does it making sense, everyone?
Yeah.
Done.
BC.
Let's check the routing table now. Show IPv6 route. You see, one I have default route, another one I have this route. Now, if you see, we got the routes, but I'll not be able to ping. Okay, let us finish R3, then we'll come and talk about that story. On R3, same procedure. On R3, to reach 1 colon D, IPv6 route, to reach 1 colon D slash 128, you need to go to 2000 colon CD colon 4. For rest, where should I go? Router 2. 2000 colon D BC
2000 colon BC.
colon 2. That is it. Actually, we have a route for every destinations now, but when I try to ping 1 colon D, the ping will not happen. In Cisco, the IPv6 routing is not enabled by default. That is the reason. See, command and all it will accept, but routing service is not enabled. How do you know that? You can know that by going to an interface and checking this interface F00 show IPv6 F0/0. See, there is a multicast address called FF02::1 only. In IPv4 world, we did not speak about multicast address for pinging. The reason is it was enabled there by default already. But in IPv6 we have, I repeat, in IPv4 we did not speak about multicasting for pinging. Because the multicasting224:2001 and 224:002 was enabled there by default. You see, this address is equal to 224:001. This is host multicasting. You need 224:002 to ping, to route. This is enabled on every interface IPv4. But in IPv6, see, FF02::2 is not enabled. So what we have to do is we need to put this command to enable IPv6 unicast routing. Very important. This enables IPv6 routing. Now, after giving this command, let me take you back. Now you will find the difference. You see, earlier it was only this. Now you have this also, FF02::2. You need to put this on every router in the path where routing is needed. IPv6 unicast routing. After giving this command, when you ping, it will ping. Okay. Now you will see a surprise. I just enabled routing, but when I ping, it will immediately ping. Not even single packet lost. If it is IPv4, it would have lost 2 or 3 packets to learn MAC address, ARP discovery. But in IPv6, you see, I'm pinging for the first time from this end to that end. It didn't take any time. It just boom. Because before you ping, it has already discovered automatically behind the screen background. Whereas in IPv4, only when you try pinging, it will provoke ARP. And it will wait for ARP reply. It takes time. Here, before you do anything, as soon as the interface comes up, the ICMP version 6 starts the job, discovery job. We are able to ping from this end to that end. All right, I think we'll stop here. We'll continue this